Imagine that an advanced industrial civilization existed on Earth millions of years before human beings appeared. Would we be able to find it? Most people assume the answer is obvious. Of course, we would know. We have dug through mountains, drilled into the ocean floor, and cataloged the bones of creatures that died hundreds of millions of years ago. Surely a civilization with cities, machines, and energy production would leave something behind that we could not miss. The surprising truth is that this assumption may be wrong. In the year 2018, a climate scientist and an astrophysicist published a serious academic paper asking exactly this question. They were not proposing that such a civilization existed. They were asking something more careful and more unsettling. If one had existed in the deep past, what evidence would actually survive, and would we recognize it if we found it? This idea has become known as the Silurian hypothesis. It is not really a claim about ancient lizard people or lost empires. It is a thought experiment about the limits of geology, the fragility of the physical record, and the difference between something being absent and something being undetectable. The reasoning behind it forces us to confront how little of the past survives at all. And once you follow that reasoning to its conclusion, it does not stop at Earth. It reaches outward to every silent planet we have ever observed. Because if our own world could hide such a secret, then the universe itself might be full of dead worlds whose stories were erased long before anyone arrived to read them. To understand why the question is so difficult to answer, we have to begin with time itself, and specifically with a kind of time that the human mind is not built to comprehend. We live our lives on the scale of days and years. A long human life spans perhaps 80 or 90 years. The span of recorded human history, from the first written tablets to the present, covers only about 5,000 years. The whole of our species, anatomically modern humans, reaches back roughly 300,000 years. These numbers already feel large. They stretch beyond anything we can personally experience. And yet, against the backdrop of the planet itself, they are almost nothing at all. The Earth is approximately 4.5 billion years old. To grasp the difference between thousands of years and billions of years, it helps to compress that enormous span into something familiar. Imagine the entire history of the planet condensed into a single calendar year, beginning at midnight on the 1st of January and ending at midnight on the 31st of December. On that scale, the Earth forms in the opening seconds of January. For months, almost nothing happens that we would recognize as life. Simple single-celled organisms appear in late winter and spring, but they remain microscopic and unremarkable for an astonishingly long stretch. Complex life, the kind with bodies and organs and movement, does not arrive until November. The dinosaurs, which feel impossibly ancient to us, appear in the middle of December and are wiped out around the 26th. And human beings, our entire genus, do not show up until the evening of the 31st of December. Recorded history, all of it, occupies the final minute before midnight. Everything you have ever read about, every empire, every war, every invention, happens in the last 60 seconds of the year. This compression reveals something important. The portion of Earth's history that humans have occupied is vanishingly small. If an industrial civilization had risen and fallen at some earlier point on that calendar, say back in October or even in late November, it would be separated from us not by thousands of years, but by tens or hundreds of millions of years. And that gap in time is the heart of the problem, because time is not a passive thing. It does not simply pass while the evidence sits patiently waiting to be discovered. Time actively destroys. The longer the interval, the more thoroughly the past is dismantled, buried, melted, and scattered. Consider what survives from genuinely ancient periods of Earth's history. We know that life existed billions of years ago, but our knowledge of those eras is extraordinarily thin. For the first half of the planet's existence, the record consists largely of chemical traces and the layered structures left by microbial mats. There are no detailed snapshots of individual organisms, no preserved landscapes, no intact ecosystems. Even when we move forward into the age of complex animals, The record remains fragmentary in ways that surprise people who have not studied it closely. The fossils that fill museum halls represent an almost unimaginably small sample of everything that once lived. The overwhelming majority of creatures left no trace at all. They lived, they died, and their bodies were recycled completely, returning to the soil and the sea without leaving any durable mark. This is the first and most fundamental obstacle. We tend to imagine the geological record as a kind of complete library, where every chapter of the past is shelved and available if only we look hard enough. But the reality is closer to a library that has suffered repeated fires, floods, and lootings over millions of years, leaving behind only scattered pages, most of them torn and faded. From those scattered pages, paleontologists and geologists reconstruct the history of life with remarkable skill. But reconstruction is not the same as completeness, and the gaps are far larger than the surviving fragments. There is another dimension to this that makes the situation even more striking. Our knowledge of the deep past is biased towards certain kinds of things. Hard structures preserve better than soft ones, which is why we have abundant fossils of shells, bones, and teeth, but almost nothing of jellyfish, worms, and the soft tissues of most organisms. Environments that bury material quickly, such as the bottoms of lakes and shallow seas, preserve far more than dry uplands where remains are exposed to the air and quickly destroyed. The fossil record, in other words, is not a random sample of the past. It is a heavily filtered selection, skewed toward hard parts, toward aquatic settings, and toward the rare moments when conditions happen to favor preservation. Anything that fell outside those narrow windows simply vanished. Now, apply this to the question at hand. A civilization, even an advanced one, exists for a relatively brief span compared to the lifetime of a planet. Human industrial society, the period in which we have built cities at scale, burned fossil fuels in enormous quantities, and produced synthetic materials, has lasted only a few centuries so far. If we generously imagine an ancient civilization persisting for 100,000 years, an immense duration by human standards that is still only a thin sliver of geological time, it would correspond to a layer of sediment perhaps a few centimeters thick or even thinner, depending on where it was laid down. Finding that specific layer in a specific location that happened to capture the right kind of evidence and recognizing it for what it is a challenge of staggering difficulty. The authors of the Silurian hypothesis understood this clearly. One of them, a climate scientist who studies the Earth's atmosphere and oceans across long timescales, was working on questions about past climate events. The other, an astrophysicist who thinks about the search for life beyond our planet, was interested in how we might detect distant civilizations. The two questions turned out to be deeply connected. To know whether we could detect an alien civilization on a faraway world, it helps to ask whether we could even detect a vanished civilization on our own. If the answer to the second question is uncertain, then our confidence about the first becomes much weaker. It is worth pausing on the name itself because it has caused some confusion. The hypothesis is named after a fictional reptilian species from an old science fiction television program, not after any real claim about ancient reptiles. The actual geological period, called the Silurian, which occurred over 400 million years ago, was a time long before any complex land animals capable of building anything existed. The name is essentially a piece of scientific humor, a nod to imagination rather than a literal proposal. The serious content of the hypothesis has nothing to do with lizards and everything to do with the fundamental limits of detection across deep time. What makes the idea so compelling is that it does not rely on any extraordinary assumptions. It does not require us to believe that such a civilization existed. It simply takes the known facts of geology and the known behavior of the physical record and follows them to a logical conclusion. The conclusion is humbling. The deep past is not an open book. It is a place we can glimpse only in fragments through a record that grows thinner and more uncertain the further back we look. And within that thinness, entire chapters could be missing without leaving any obvious gap, because we have no way of knowing what should have been there in the first place. This sets up the central tension that runs through everything that follows. On one side stands our intuition, which insists that something as significant as a civilization could never be lost. On the other side stands the hard reality of how the planet preserves and destroys its own history. These two things pull in opposite directions, and resolving the tension requires us to look much more closely at exactly how the geological record forms, what it captures, and what it inevitably loses. Before we can ask whether an ancient civilization would leave a mark, we first have to understand what kinds of marks the Earth is capable of keeping. And that means turning to the precise question the two scientists set out to answer, a question that sounds simple, but opens into something far larger than it first appears. The question that the two scientists posed in their paper was deceptively plain. Phrased in everyday language, it asked whether it would be possible to detect an industrial civilization in the geological record if that civilization had existed far enough back in time. But behind that single sentence lay a careful reframing of how we think about both the past and the search for life elsewhere. The brilliance of the question was not that it suggested something hidden in Earth's history. It was that it exposed a blind spot in our reasoning that almost no one had examined directly. To appreciate why this reframing mattered, it helps to understand the context in which the question arose. Both authors were thinking about the search for life on other planets, a field that has grown enormously in recent decades. We now know that planets are common throughout the galaxy. Telescopes have identified thousands of worlds orbiting other stars, and statistical estimates suggest that the number of planets in our galaxy alone runs into the billions. Among those, a meaningful fraction lie in the zone around their stars where liquid water could exist, the condition most associated with life as we understand it. This abundance has intensified one of the oldest questions humans have asked. If planets are so common, and if many of them could support life, then where is everyone? Why does the universe appear so silent? This silence has a name and a long history of debate. The puzzle is often framed as a contradiction between the apparent likelihood of life and the complete absence of any confirmed sign of it elsewhere. Many explanations have been offered. Perhaps life is far rarer than the abundance of planets suggests. Perhaps intelligence is rarer still. Perhaps civilizations tend to destroy themselves shortly after arising. Perhaps they are out there, but too distant, too brief, or too different for us to notice. Each of these explanations carries assumptions, and the Silurian hypothesis quietly challenges one of those assumptions in a way that had been largely overlooked. The overlooked assumption is this: when we search for evidence of a past civilization, whether on another world or in our own deep history, we implicitly assume that such a civilization would leave behind clear, lasting, recognizable traces. We assume that the record is durable, that significant events imprint themselves permanently, and that absence of evidence can be read as evidence of absence. The two scientists set out to test that assumption against the actual behavior of geology, and they used Earth itself as the test case precisely because Earth is the one planet whose history we know in the greatest detail. If our confidence breaks down even here, on the world we understand best, then it should break down even more dramatically for distant planets we can barely observe. There was also a personal and practical origin to the question, which the climate scientist among them has described. Much of his work involved studying ancient episodes of rapid climate change, events in which the planet warmed dramatically over relatively short spans of geological time. In examining these events, he noticed something that gave him pause. The chemical fingerprints of these ancient warming episodes bore an unsettling resemblance to the fingerprints that human industrial activity is leaving in the present day. Both involve the rapid release of carbon into the atmosphere and ocean, and both produce measurable shifts in the chemistry of the rock and sediment that formed during those intervals. This raised a thought that he could not easily dismiss. When we look at an ancient warming event and attribute it to natural causes, are we certain it was natural? Or could a similar signal, in principle, arise from the activity of a civilization we have no other way of knowing about? He was careful, and the paper was careful, to make clear that there is no actual evidence for such a thing. The ancient warming events we know about are fully consistent with natural explanations, and there is no reason to suspect otherwise. But the resemblance was instructive. It demonstrated that the kind of signal a civilization produces does not necessarily look distinctive in the record. It can look like a natural disturbance. It can be mistaken for or indistinguishable from processes that have nothing to do with intelligence. This is a crucial insight, because it means that even if traces survive, they might not announce themselves as artificial. They might blend into the background of ordinary geological change. From this starting point, the question expanded into a structured investigation. To ask whether a civilization would be detectable, you first have to define what a civilization actually leaves behind. The authors recognized that the most durable consequences of an industrial society are not its objects, but its byproducts. Cities crumble, machines corrode, and individual artifacts are exceedingly unlikely to survive across millions of years. What lasts longer are the broad planet-wide changes that industrial activity causes. These include shifts in atmospheric chemistry, alterations in the distribution of certain elements and isotopes, the introduction of entirely new synthetic substances, and changes in the rates at which sediments accumulate and species go extinct. The question then is whether any of these broad signatures would persist long enough and clearly enough to be identified by a future investigator, or by us looking backward into the deep past. This shift in focus from objects to signatures is one of the most important moves in the entire argument. It mirrors exactly how scientists approach the search for life on other planets. We do not expect to find alien buildings through a telescope. Instead, we look for chemical imbalances in atmospheres, unusual combinations of gases, or other patterns that could indicate biological or technological activity. The Silurian hypothesis applies the same logic in reverse and across time rather than across space. It asks what chemical and physical imbalances a civilization would create, and whether those imbalances would still be visible after tens of millions of years of geological processing. The framing also introduced a careful distinction between two very different things, a distinction that becomes central later in the reasoning. There is the question of whether a civilization existed, and there is the entirely separate question of whether we could detect it if it had. These are not the same. A civilization could have existed and left detectable traces. It could have existed and left no detectable traces. It could have never existed at all. When we look at the record and find nothing, we cannot immediately tell which of these situations we are in. The empty record is consistent with multiple explanations, and distinguishing between them requires understanding the limits of detection, not just the contents of the rock. This is why the hypothesis is fundamentally a thought experiment about epistemology, about the nature and limits of what we can know, rather than a historical claim. It does not assert that the deep past contained civilizations. It asserts that our ability to rule them out is weaker than we assume, and it sets out to measure exactly how weak that ability is. In doing so, it provides a kind of calibration for the broader search for life. If we can quantify how easily Earth could hide a vanished civilization, we gain a better sense of how much weight to place on the silence we observe across the galaxy. The two researchers approached this with the tools of their respective fields. The climate scientist brought detailed knowledge of how carbon, nitrogen, and other elements cycle through the atmosphere, ocean, and rock, and how those cycles register in the sedimentary record. The astrophysicist brought a framework for thinking about civilizations in general terms, about the kinds of energy use and material production that any technological society might engage in, regardless of its specific form. Together, they built an argument that was neither sensational nor dismissive. It took the question seriously enough to examine it rigorously, while remaining grounded in established science at every step. What emerged from their analysis was a sobering picture. The traces a civilization leaves are real, but they are subtle and they fade. The record that would have to preserve them is thin, biased, and constantly being destroyed. And the act of recognizing such traces, even if they survived, would require us to distinguish them from natural processes that can mimic them closely. Each of these obstacles deserves close examination because together they determine whether the deep past could be hiding something we have never noticed. But before we can evaluate what signatures might survive, we have to confront the most basic obstacle of all, the one that destroys most evidence before any of these subtler questions even come into play. We have to understand just how unlikely it is for anything at all to be preserved across geological time. Because the first thing that happens to almost everything that has ever existed on this planet is not preservation. It is erasure, swift and nearly total. And the rare exceptions, the things that do survive, owe their survival to a chain of coincidences so improbable that it amounts to something like a lottery. The chance that any given organism becomes a fossil is so small that it is difficult to express in ordinary terms. When an animal dies, the most common outcome by far is complete destruction. Scavengers consume the soft tissues and scatter the bones. Bacteria and fungi break down whatever remains. Exposure to air, water, and temperature swings accelerates the decay. Within a remarkably short time, often a matter of weeks or months, a body that was once a living creature is reduced to nothing that will last. The atoms that composed it are recycled into the soil, the water, and other organisms. Nothing is preserved. This is the fate of the overwhelming majority of all creatures that have ever lived. They leave the world as completely as if they had never been part of it. Fossilization is the rare exception to this rule, and it requires a specific and unlikely sequence of conditions. First, the remains must avoid being eaten or scattered, which usually means rapid burial. An animal that dies and is quickly covered by sediment, perhaps by being swept into a river and buried in mud, or by sinking to the still bottom of a lake or sea, has a far better chance than one that dies in the open air. Second, the burial environment must protect the remains from oxygen and from the organisms that drive decay, conditions most often found in waterlogged low oxygen settings. Third, over long periods, the surrounding sediment must harden into rock, and minerals dissolved in groundwater must gradually replace or fill the original material, turning bone and shell into stone while preserving its shape. Fourth, this rock must then survive for however long it takes, often hundreds of millions of years, without being eroded away, melted by the planet's internal heat, or crushed and deformed beyond recognition. And finally, the fossil must end up somewhere accessible, exposed at the surface or reachable by drilling, at a moment when someone is there to find it and able to recognize what it is. Each of these steps filters out the vast majority of candidates. The result is that the fossil record, impressive as it is, captures only a minuscule fraction of past life. Estimates vary, but it is clear that the creatures we have discovered represent a tiny sample of the total diversity that has existed. Entire groups of organisms are known from a single specimen or from fragments. Some are inferred to have existed only because of indirect traces with no body fossils at all, and countless others, perhaps the majority, have left no trace whatsoever and will never be known. The history of life that we have reconstructed is real and reliable in its broad outlines, but it is built from scattered survivors of an enormous and continuous loss. This filtering is not random in its effects. It systematically favors certain kinds of organisms and certain kinds of environments, which distorts our picture of the past in predictable ways. Hard parts preserve far better than soft ones. An animal with a shell, a skeleton, or teeth has a much higher chance of leaving a fossil than a creature made entirely of soft tissue. This is why our knowledge of ancient marine life is dominated by shelled organisms, and why soft-bodied creatures are known only from a handful of exceptional sites where unusual conditions preserve them. It is also why the early history of animal life remains so murky. Before hard parts became common, organisms were almost entirely soft-bodied, and their preservation required extraordinary circumstances that occurred only rarely. Environment matters just as much as anatomy. Aquatic settings, especially the floors of seas and lakes, are ideal for fossilization because sediment accumulates steadily there and burial happens naturally. Land environments are far less favorable. On dry land, Remains are exposed to scavengers, weather, and erosion, and there is often no steady deposition of sediment to bury them. As a result, the fossil record is heavily skewed toward life in and around water, and our knowledge of purely terrestrial organisms is correspondingly thinner. Creatures that lived in mountains, deserts, or upland forests, far from any depositional basin, are dramatically underrepresented because the very places they lived were places where preservation almost never occurred. There is a further subtlety that bears directly on the question of detecting a civilization. Fossilization preserves form, the shape of bones and shells, but it does so over geological time only for objects that happen to fall within the narrow band of preservable conditions. A civilization's most numerous and distinctive objects, its buildings, tools, vehicles, and devices, are made of materials and exist in settings that are mostly hostile to long-term preservation. Cities are typically built on land, in elevated and exposed locations, exactly the kind of environment where erosion dominates and burial is rare. The materials of an industrial society, metals, concrete, glass, and synthetic compounds, are durable on human timescales, but vulnerable on geological ones. Metals corrode and dissolve, concrete weathers and crumbles. Glass, though chemically stable, fractures and disperses. Across millions of years, these materials would not endure as recognizable artifacts. They would break down, scatter, and ultimately be either eroded away or, in rare cases, reduced to chemical traces in sediment. This is a point worth dwelling on because it runs so strongly against intuition. We look at our monumental structures, our bridges and skyscrapers and highways, and we cannot imagine them simply disappearing. They feel permanent. But permanence is a matter of time scale. On the scale of a human life, or even of recorded history, these structures seem indestructible. On the scale of geological time, they are ephemeral. The same forces that grind mountains down to sand and carve canyons out of solid rock would, given enough time, dismantle everything we have built, and the products of that dismantling would not remain as a neat layer of recognizable rubble. They would be transported, sorted, mixed, and dispersed by water and wind, eventually losing any obvious sign of their origin. Consider a single illustrative case. Among all the dinosaurs that ever lived, across many millions of years and countless individuals spread across the entire planet, we have recovered only a limited number of specimens, and complete skeletons are genuinely rare. The most famous and well-studied dinosaur species are known from a handful of good specimens, sometimes fewer. If creatures that dominated the planet for such an enormous span, in such vast numbers, with durable bones well-suited to fossilization, left behind so sparse a record, then we should think carefully about what a civilization lasting a few thousand or even a few 100,000 years would leave. A civilization is not spread evenly across the planet for tens of millions of years. It is concentrated in time and, relative to geological spans, exceedingly brief. Its physical footprint, however dramatic it seems to its inhabitants, is a thin slice in the sedimentary column, easily lost among the far thicker layers above and below it. The probability mathematics of preservation therefore work strongly against the survival of direct recognizable artifacts. This does not mean that nothing would survive. It means that the survival of obvious objects, the kind that would unambiguously announce a civilization, is extremely unlikely. What might survive instead are the indirect consequences, the chemical and physical alterations that industrial activity imposes on the planet as a whole. These are not objects that can be eroded away in one place. They are global changes recorded across many locations, and that breadth gives them a better chance of leaving a detectable mark. The fossil lottery destroys individual things, but planet-wide chemical shifts are harder to erase completely because they are written into the very composition of the sediments forming everywhere at once. This reframing from artifacts to global signatures is what keeps the question scientifically alive, rather than dismissing it outright. If we were looking only for fossilized machines or buried cities, the answer would be straightforward and pessimistic. The chance of finding such things across deep time is negligible. But the inquiry does not depend on finding objects. It depends on detecting the fingerprints that large-scale energy use and material production leave in the chemistry of the Earth. And those fingerprints behave differently. They are subtler, but in some ways more durable, because they are not confined to a single vulnerable structure. They are smeared across the planet, carried by air and water into countless depositional environments where some fraction of them might be preserved. So the lottery of fossilization, brutal as it is, does not close the question. It shifts it. It tells us that we should not expect to dig up the remains of an ancient industrial society in any direct form. The bodies, the buildings, and the machines are almost certainly gone, dissolved into the relentless recycling of the planet's surface. But it also tells us where to look instead. If anything remains, it will not be in the shape of objects. It will be in the composition of the rock, in ratios of elements and isotopes that ordinary processes would not produce, in the faint chemical echo of activity that once changed the whole world. To understand whether such echoes could survive, we first need to see clearly what happens to the physical structures of a civilization once the civilization itself is gone, and how quickly the familiar landscape of human construction would return to something unrecognizable. Picture the world emptied of people all at once, with everything we have built left standing exactly as it is. No maintenance, no repairs, no one to pump water out of basements or clear debris from drains or repaint surfaces against the weather. From that first day, the slow dismantling begins, and the timeline of decay reveals just how dependent our constructed environment is on constant human attention. Within days, the most managed systems fail. Underground railways and tunnels, which are kept dry only by continuous pumping, begin to flood as groundwater seeps in unchecked. The pumps that hold back this water require power and oversight, and without them, the lowest levels of cities fill quietly with water within a few days. Within months, the consequences spread upward and outward. Fires, sparked by lightning or electrical faults or accumulated fuel, burn unchecked because there is no one to extinguish them, and they consume neighborhoods that would once have been saved. Without heating in cold climates, water trapped in pipes and within building materials freezes, expands, and cracks the structures around it. Roofs, once breached by a single failed seal or a fallen branch, begin to let in rain. And water is the great enemy of every building. Once water penetrates a structure, it accelerates every other form of decay, rotting wood, rusting steel, and dissolving the bonds that hold materials together. Within years, plants take over. Seeds carried by wind and animals find purchase in the cracks of pavement and the gaps in walls. Roots pry apart concrete and masonry, widening every fissure. Vegetation reclaims roads, parking areas, and open spaces, breaking the hard surfaces into fragments that soil and moisture can infiltrate. The clean lines of the built environment soften and blur as green growth covers them. Animals move into the spaces we have abandoned, and the boundary between city and wilderness dissolves. What was recently a place of order and control becomes, within a decade or two, a landscape in the early stages of returning to a natural state. Within decades, the larger structures begin to fail in earnest. Steel, the material that makes tall buildings and long bridges possible, is fundamentally vulnerable to corrosion. The steel reinforcement embedded in concrete rusts as water reaches it, and as it rusts, it expands, cracking the concrete from within and weakening the entire structure. Bridges, deprived of inspection and repair, lose their integrity and eventually collapse under their own weight or under the force of floods and storms. Buildings whose frames are compromised begin to lean, buckle, and fall. The process is not uniform, and some structures last longer than others, but the overall direction is unmistakable. The tallest and most ambitious constructions, the ones that required the most engineering to stand, are often among the first to come down because they depend most heavily on the integrity of materials that decay. Within centuries, most of what we recognize as a city would be gone or unrecognizable. Wooden structures would have rotted away entirely. Steel frames would have rusted into fragments. Concrete, though more durable, would have cracked, spalled, and crumbled, especially where reinforcement within it had corroded. Glass would have shattered and scattered. The materials would not vanish instantly, but they would lose their form, breaking into rubble that vegetation and soil progressively bury. The grid of streets, the outlines of foundations, the shapes of buildings would fade beneath accumulating layers of organic material and wind-blown sediment. A person walking through such a place after several centuries would see mounds and irregularities, perhaps, but little that clearly announced a sophisticated civilization. And this is only the span of centuries, an eye blink compared to the timescales relevant to the Silurian hypothesis. The question is not what survives after hundreds of years, but what survives after millions. On that scale, the picture changes from decay to something more thorough. Erosion, the steady removal of material by water, wind, and ice, would not merely bury the remains of a civilization. In many places, it would strip them away entirely, carrying the broken fragments downhill, into rivers, and ultimately toward the sea, where they would be deposited as sediment, mixed with everything else, and gradually compressed into rock. The very land on which a city stood might itself be worn down and removed, exposing older rock beneath and leaving no surface trace of what had been there. In other places, the opposite would happen. Material would not be stripped away, but buried under accumulating sediment, layer upon layer, sinking deeper over time. This burial is, paradoxically, the only path toward long-term preservation, but it transforms whatever is buried beyond easy recognition. The pressure of overlying sediment compresses the buried material. Heat from the depths alters its chemistry. Groundwater dissolves some components and deposits others. Over millions of years, what began as the remains of a structure becomes part of the rock itself, its original substances chemically transformed, its shape distorted, its identity as an artifact largely erased. If anything of a civilization survives that long, it survives not as a thing, but as a stain, a chemical anomaly, a subtle difference in the composition of a layer of stone. It is worth being precise about the difference between burial and preservation, because they are often confused. Burial is necessary for preservation, but it is not sufficient. Most buried material is eventually destroyed anyway, either by the chemical and physical changes that occur with depth and time, or by being caught up in the slow churning of the planet's crust. Only a small fraction of buried material survives in any recognizable form, and that fraction depends heavily on the specific conditions of burial. The same logic that governs fossilization governs the preservation of everything else. The conditions must be just right, and they rarely are. There is also the matter of how thin the layer would be. A civilization, even a long-lasting one, occupies a brief interval of geological time. The sediment deposited during that interval in any given location would be a thin band, perhaps a few centimeters or less, sandwiched between the much thicker accumulations of the eras before and after. Within that thin band, the evidence of the civilization would have to be concentrated, and that band would have to survive the subsequent millions of years of burial, compression, heating, and potential erosion, and then happen to be exposed or accessible at a moment when someone was looking. The odds at each stage are poor, and they compound. The chance of a recognizable artifact making it through every stage approaches the negligible. This is why the focus shifts once again and decisively away from objects and toward chemistry. Objects do not survive, but chemical changes, especially those spread across the entire planet, behave differently. When a civilization burns enormous quantities of buried carbon, alters the balance of elements in the atmosphere and ocean, and introduces novel substances, these changes are not confined to one vulnerable location. They are recorded faintly in sediments forming everywhere at once, in the deep ocean as well as on the continents, in countless places that experience different fates over geological time. Even if most of those records are later destroyed, some fraction may survive, precisely because the signal was global rather than local. The destruction of any single site does not erase a planet-wide signature, because the same signature is being written in many places simultaneously. So the disappearance of cities, total as it would be, does not by itself answer the question. It eliminates one category of evidence, the direct and obvious kind, while leaving open another, the indirect and chemical kind. To evaluate whether that second category could survive and be recognized, We have to understand how the geological record actually stores chemical information. We have to learn how layers of rock function as a kind of archive, how that archive is written, and what kinds of signals it is capable of holding across the immense spans of time that the question demands. The buildings are gone, but the rock remembers more than the buildings ever could, and learning to read that memory is the next step in understanding what the deep past might or might not be hiding. Geologists treat layered rock as a written record, and the comparison to writing is more than a convenient image. Sedimentary rock forms in layers, one deposited atop another over time, and because newer layers settle on top of older ones, the sequence preserves a chronological order. The deeper you go in an undisturbed sequence, the further back in time you travel. This simple principle, that lower layers are generally older than the layers above them, is one of the foundations of geology. It allows the layered rock exposed in a canyon wall or recovered in a drilled core to be read like the pages of a book, from bottom to top, oldest to youngest. Each layer is a page, and the contents of that page record something about the conditions under which it formed. What gets written on each page depends on what was settling out of the water or air at that time and place. In a calm sea, fine particles drift slowly down and accumulate as mud that later hardens into shale. In a fast-moving river, coarser sand is carried and deposited, later becoming sandstone. Where shelled organisms thrive and die, their remains pile up and form limestone. The type of rock, its grain size, its color, and its composition all carry information about the environment that produced it. A geologist reading a sequence of layers can reconstruct a history of changing conditions, of seas advancing and retreating, of climates shifting, of rivers migrating across the land. The rock is not just a passive record. It is an actively informative one, encoding the circumstances of its own formation. Within these layers, beyond the rock type itself, finer signals are preserved. Chemical elements settle into the sediment, their proportions reflecting conditions in the water and atmosphere. The remains of organisms, even when not preserved as visible fossils, leave chemical traces. Particles carried from distant volcanic eruptions or dust storms appear as distinctive bands. Each of these contributes to the record, layering information upon information. The result is a dense archive in which a single thin slice of rock can contain many overlapping kinds of evidence about the world as it was when that slice formed. Learning to extract this information is much of what the science of reading the rock record involves, but the archive has limitations that are essential to understand because they bear directly on whether a brief ancient signal could be detected. The first limitation is that the record is not continuous. Sediment does not accumulate steadily and without interruption in any one place. There are long periods when no sediment is deposited at all, or when previously deposited sediment is eroded away before it can be buried and preserved. These gaps, where time has passed but left no layer to mark it, are extremely common. In fact, in most locations, the gaps account for far more time than the preserved layers do. A sequence of rock that looks continuous can contain enormous missing intervals, periods of millions of years that simply are not represented because nothing was preserved from them. The record is less like a complete book and more like a book with most of its pages torn out, where the surviving pages give no indication of how many are missing between them. This discontinuity has a profound implication for the question at hand. If a civilization existed during one of these missing intervals in a particular location, there would be no layer to record it there at all. The page would simply be absent. And because the gaps are so common and so large, the chance that any given location preserved a continuous record spanning the exact brief interval of a hypothetical civilization is low. The signal could fall entirely within a gap, leaving no trace, not because the civilization left nothing, but because that particular archive skipped over the time when it existed. This is why scientists rely on multiple locations and multiple records. No single archive is complete, but by combining many partial records from around the world, they can piece together a more continuous picture, filling the gaps in one place with the preserved intervals from another. The second limitation concerns resolution, the fineness of detail the record can capture. The rate at which sediment accumulates varies enormously, from less than a millimeter per thousand years in some deep ocean settings to much faster rates in places with abundant sediment supply. Where accumulation is slow, a great deal of time is compressed into a thin layer, and brief events become impossible to distinguish. A century, or even a millennium, might be represented by a layer too thin to sample separately, its contents blended with the centuries before and after. This blurring means that short-lived events, no matter how dramatic, can be smeared out and lost in the averaging. An industrial period lasting only a few centuries, deposited in a slowly accumulating setting, might leave a layer thinner than the resolution at which we can read the record, its signal averaged into invisibility. This matters because a civilization, by geological standards, is a short event. Even a long-lasting one occupies a span that, in many depositional settings, would be compressed into a thin and possibly unreadable layer. To detect such a brief signal, you need a setting where sediment accumulated quickly enough to spread the relevant interval across a thick enough layer to be sampled in detail. Such settings exist, but they are not universal, and they bring their own complications. Rapidly accumulating sediments are often found in environments that are themselves disturbed, reworked, or unlikely to be preserved over very long timescales. There is a tension here. The settings best suited to recording a brief event in detail are not always the settings best suited to surviving for hundreds of millions of years. The third limitation is alteration after deposition. Once sediment is buried, it does not remain unchanged. Chemical reactions continue, driven by the heat and pressure of burial and by the movement of groundwater through the rock. These reactions can dissolve original components, introduce new ones, and shift the proportions of elements and isotopes. A chemical signal present when the sediment formed can be modified, diluted, or obscured by these later processes. Reading the record therefore requires not just measuring what is present, but understanding how it might have changed since deposition and correcting for those changes. The deeper and older the rock, the more it has been altered and the harder it becomes to recover the original signal with confidence. Despite these limitations, the rock record remains an extraordinary tool, and geologists have developed sophisticated methods to extract reliable information from it. They cross-check multiple records against one another. They use known events such as well-dated volcanic ash layers or shifts in the planet's magnetic field as reference markers to align records from different locations. They measure many different chemical signals and look for patterns consistent across them. Through these methods, they have reconstructed the history of the planet's climate, its oceans, its atmosphere, and its life across hundreds of millions of years, with impressive detail for the more recent past and decreasing but still meaningful detail for the deeper past. The archive is incomplete and imperfect, but it is far from empty, and it has yielded a vast and reliable understanding of Earth's history. The key question for the Silurian hypothesis is whether the kinds of signals a civilization would produce fall within the range that the record can preserve and that we can read. And the answer, as the analysis shows, is nuanced. Some signals would be too brief, too localized, or too easily altered to survive in readable form. Others, particularly global chemical changes that affect the entire planet and persist for a meaningful duration, have a better chance. The challenge is that even these better candidates would be subtle, and distinguishing them from natural variations would require care, and crucially, a reason to look in the first place. We tend to find what we are searching for, and no one searching the record for natural climate history would necessarily recognize an artificial signal embedded within it, especially if that signal resembled a natural one. This brings us to a specific and powerful class of evidence, one that survives better than almost anything else, and that lies at the heart of how the rock record stores information about the chemistry of the past. Long after objects have vanished, and even after many chemical signals have faded, certain atomic signatures can persist, locked into the sediment as measurable ratios that reflect conditions at the time of formation. These signatures are the whispers the record retains when nearly everything else has been lost, and they are precisely the kind of evidence that a civilization, through its effect on the planet's chemistry, would be most likely to leave behind. Understanding what these atomic whispers are and how they survive is the next piece of the puzzle. The atoms that make up the world come in variants, and these variants are the key to reading the chemistry of the deep past. An element is defined by the number of protons in its nucleus, but the number of neutrons can vary, producing forms of the same element with slightly different masses. These variants are called isotopes. Carbon, for example, exists primarily as a lighter form and a slightly heavier form, both chemically carbon but differing in mass. Most elements have several isotopes, and the proportions in which they occur are not fixed. Different processes favor different isotopes, subtly shifting the ratios in ways that depend on what is happening physically and biologically. Because these shifts are recorded in the sediment that forms at any given time, the ratio of isotopes preserved in rock becomes a kind of chemical fingerprint of the conditions that produced it. The reason isotope ratios are so valuable is that they survive when almost everything else has been destroyed. The proportion of one isotope to another is a property of the atoms themselves, written into the chemistry of the rock at the level of individual elements. While shapes erode and structures crumble and many compounds break down, the ratio of carbon isotopes locked into a layer of sediment can persist for hundreds of millions of years, because it is not dependent on the survival of any particular object or structure. It is dependent only on the survival of the rock and the stability of the chemical signal within it. This makes isotopes one of the most durable forms of information about the past, and one of the primary tools geologists use to reconstruct ancient environments. Consider carbon, which is central to the question of detecting a civilization. Living organisms preferentially take up the lighter form of carbon during the chemical reactions of life, particularly photosynthesis. As a result, organic matter is enriched in the lighter isotope relative to the inorganic carbon in the environment. When organisms die and their carbon is buried, that lighter signature is buried with them. Over vast spans of time, buried organic matter, including the material that becomes coal, oil, and natural gas, carries this distinctive isotopic signature weighted toward the lighter form of carbon. This is a crucial detail because it means that the carbon stored in fossil fuels is chemically marked in a way that distinguishes it from the carbon circulating in the atmosphere and ocean. Now, consider what happens when a civilization burns those fossil fuels on a large scale. The buried carbon, enriched in the lighter isotope, is released back into the atmosphere as carbon dioxide. This influx of light carbon shifts the overall isotopic balance of the atmosphere and ocean toward the lighter form. The shift is measurable, and because it affects the entire planet's carbon system, it is recorded in sediments forming everywhere during that interval. Marine organisms building their shells incorporate carbon from the water, and the isotopic ratio of that carbon reflects the shifted balance. When those organisms die and their shells accumulate in sediment, the isotopic signature is locked in. Millions of years later, that signature can in principle still be read, a faint chemical record of a time when an unusual amount of light carbon entered the system rapidly. This is precisely the kind of signal that links the present to the deep past in a troubling way. Human industrial activity is currently producing exactly such a shift. By burning fossil fuels, we are releasing buried light carbon into the atmosphere at a rapid rate, and this is altering the isotopic composition of the global carbon system in a way that will be recorded in the sediments forming now. A future investigator reading those sediments would find a rapid shift toward lighter carbon coinciding with other changes, and that pattern would be a candidate signature of industrial activity. The question the Silurian hypothesis raises is whether a similar signature produced by a hypothetical ancient civilization might already exist somewhere in the record, and whether we would recognize it for what it was if we found it. The complication is that natural processes can also produce shifts in carbon isotope ratios. The carbon cycle is dynamic, and various natural events can release large amounts of carbon, including light carbon, into the atmosphere and ocean over relatively short spans. Volcanic activity, the destabilization of carbon-rich deposits, and changes in the patterns of ocean circulation can all leave isotopic signatures. This means that finding a carbon isotope shift in the record does not by itself indicate a civilization. It indicates a disturbance in the carbon cycle, which could have many causes. Distinguishing an artificial cause from a natural one requires looking at additional features of the signal, such as how rapidly it occurred, what other changes accompanied it, and whether the pattern matches what natural processes typically produce. Carbon is not the only element whose isotopes carry information. Nitrogen isotopes reflect changes in biological productivity and in the cycling of nutrients, and large-scale agriculture and industrial processes alter the nitrogen cycle in ways that could leave isotopic traces. The production of synthetic fertilizer, which fixes atmospheric nitrogen into forms that plants can use, represents a massive human intervention in the nitrogen cycle, and it shifts nitrogen isotope ratios in soils and sediments. Other elements, too, have isotopic systems that respond to specific processes, and each provides a different window into past conditions. By measuring multiple isotopic systems together, scientists can build a more detailed and constrained picture of what was happening, reducing the ambiguity that any single signal would carry on its own. There are also isotopes that are not naturally present in significant amounts, and that point unambiguously to specific kinds of activity. Certain isotopes are produced only by particular nuclear processes, and their presence in the environment, in quantities beyond what natural processes generate, would be a strong indicator of technological activity involving nuclear reactions. This is a different kind of signal from the carbon shift, because rather than being an amplification of a natural pattern, it is the introduction of something that would otherwise be rare or absent. Such isotopes, however, often decay over time, transforming into other elements at characteristic rates. Some decay quickly, vanishing within years or decades, while others persist for much longer. The survival of a nuclear isotope signature across geological time depends on the half-life of the specific isotope, and many of the most diagnostic ones would not last long enough to be detectable after millions of years, though their decay products might, under the right conditions, leave a subtler trace. The durability of isotopic signals varies then, depending on the element, the isotope, and the chemical environment. Carbon isotope ratios in well-preserved marine sediments can survive for hundreds of millions of years and are routinely used to study ancient events. Other signals are more fragile, subject to alteration, as the rock is buried, heated, and exposed to groundwater. The art of reading isotopic records involves understanding which signals are robust and which are vulnerable, and accounting for the ways that later processes might have modified the original ratios. For the question of detecting a civilization, the most promising signals are those that are both diagnostic, meaning they point clearly to industrial or technological activity, and durable, meaning they survive the long journey through deep time. The intersection of those two qualities is narrow, but it is not empty. What makes isotopic evidence so central to the Silurian hypothesis is that it represents the best chance of detecting an ancient civilization through its effects rather than its objects. Objects do not survive, but a global shift in carbon isotopes might. A change in nitrogen cycling might. The introduction of unusual isotopes might, at least for a time. These are the whispers the record retains, faint and ambiguous, but real. The challenge is interpretation. A shift in isotope ratios is a sign that something happened, but it does not come labeled with its cause. To attribute it to a civilization rather than to a natural event requires additional evidence and careful reasoning, and even then, the conclusion would be uncertain. The record speaks, but it speaks in a language that does not distinguish easily between the natural and the artificial. This ambiguity is best illustrated by an actual event in Earth's history. A genuine episode of rapid global change that left exactly the kind of isotopic signature we have been describing. This event was unquestionably natural, but it serves as a powerful test case because it shows what a sudden disturbance to the planet's carbon system looks like in the record, and it reveals how closely such a natural event can resemble the signature that an industrial civilization would produce. Examining this ancient warming in detail provides the clearest possible window into both the promise and the difficulty of reading the deep chemical past. Around 56 million years ago, the planet underwent a dramatic and rapid episode of warming that has become one of the most studied events in the geological record. It is known by a long technical name that scientists usually shorten to a set of initials, but the essential facts are straightforward. Over a geologically brief interval, global temperatures rose substantially by several degrees, and this warming was accompanied by major disruptions to ocean chemistry, to life on land and in the sea, and to the global carbon cycle. The event lasted, in its acute phase, for a span of thousands to tens of thousands of years, and the recovery extended over a much longer period. It stands as one of the clearest natural examples of what happens when a large amount of carbon enters the atmosphere and ocean rapidly. The reason this event is so relevant to the Silurian hypothesis is the nature of its signature in the rock record. When scientists examine sediments that formed during this warming, they find a pronounced shift in carbon isotope ratios, exactly the kind of shift toward lighter carbon that would result from a massive injection of carbon into the system. They also find evidence of ocean acidification recorded in the dissolution of carbonate sediments on the sea floor, because adding carbon dioxide to seawater makes it more acidic and dissolves the carbonate that organisms use to build their shells. They find changes in the types of organisms present, with some groups suffering extinctions while others migrated or adapted. And they find evidence of the warming itself, recorded in various chemical and biological indicators. Together, these signals paint a detailed picture of a planet responding to a sudden carbon-driven disturbance. What makes this event so instructive is how closely its signature resembles what human industrial activity is producing today. We are currently adding carbon to the atmosphere rapidly, shifting carbon isotope ratios toward the lighter form, acidifying the oceans, warming the climate, and stressing ecosystems. The parallels between this ancient event and the present are striking enough that the ancient warming is frequently studied as a natural analog for understanding the consequences of current changes. The same processes are at work, the same kinds of signals are being generated, and the same kinds of disruptions are unfolding, albeit on different timescales and at different magnitudes. The ancient event was natural, driven by the release of carbon from natural reservoirs, while the present change is driven by human activity, but the chemical fingerprints are remarkably similar. This similarity is the crux of the matter. If an industrial civilization had existed in the deep past and had burned through a large quantity of buried carbon, the signature it would leave in the record would resemble the signature of this natural warming event. A rapid shift toward lighter carbon, ocean acidification, warming, and ecological disruption, all occurring over a relatively brief interval, would be the expected result. And yet, when we find such a signature in the record, as we do for this ancient event, we attribute it to natural causes, because natural causes are sufficient to explain it, and there's no reason to invoke anything else. This raises the unsettling question the Silurian hypothesis poses. How confident can we be that every such event in the record was natural? If an artificial event would look essentially the same, then the record alone might not be able to tell us which it was. It is important to be precise about what this does and does not imply. There is no evidence that the ancient warming event was anything other than natural. The amount of carbon involved, the timescale over which it was released, and the pattern of the signal are all consistent with natural mechanisms, and scientists have proposed several plausible natural sources for the carbon, including the release of carbon from seafloor deposits and from volcanic activity. The event is not a mystery requiring an exotic explanation. The point of the comparison is not to suggest that a civilization caused it. The point is to demonstrate that the kind of signature an industrial civilization would produce is not unique. It falls within the range of signatures that natural processes can also produce, which means that the mere existence of such a signature in the record cannot, by itself, distinguish an artificial cause from a natural one. The differences that might allow such a distinction are subtle and lie in the details of the signal. One potentially distinguishing feature is the rate of carbon release. Human industrial activity is releasing carbon at a rate that appears to be faster than what occurred during the ancient warming event, and faster than most natural processes can achieve. If the rate of release could be precisely determined from the record, an exceptionally rapid release might point toward an artificial cause, because few natural processes can inject carbon as quickly as the burning of fossil fuels by an industrial society. The problem is that determining the precise rate from the record is extremely difficult, especially for events deep in the past. The blurring of the record, the gaps, and the limits of dating precision make it hard to resolve whether a release took decades, centuries, or millennia. A signal that was actually very rapid might appear, in the smeared record of deep time, to have been more gradual, masking the very feature that would distinguish it. Another potentially distinguishing feature is the combination of signals that accompany the carbon shift. A natural carbon release might not be accompanied by certain other changes that an industrial civilization would produce, such as the introduction of synthetic compounds, unusual concentrations of particular metals, or isotopic anomalies from nuclear activity. If a carbon isotope shift in the record were found alongside these other distinctly artificial signatures, the case for an artificial cause would be much stronger. The carbon shift alone is ambiguous, but the carbon shift combined with a suite of other unnatural signals would be far more telling. This is why the search for an ancient civilization, if it were undertaken seriously, would not focus on any single signal, but on the coincidence of multiple signals that together would be difficult to explain by natural means. The ancient warming event also illustrates another important point about the recovery and persistence of such signals. After the acute phase of the warming, the planet's systems gradually returned toward their previous state, but the recovery took an enormous amount of time, far longer than the initial disturbance. The carbon that had been added to the system was slowly removed through natural processes, including the weathering of rock and the burial of organic matter. But this removal operated over tens of thousands to hundreds of thousands of years. The signature of the event, however, remained locked in the sediments that formed during it, preserved well enough to be read 56 million years later. This demonstrates that a carbon-driven disturbance can leave a durable mark, one that survives across vast spans of time and remains legible to careful investigation. If the ancient warming left such a mark, then an industrial civilization producing a similar disturbance would also leave a mark, at least in principle. But the persistence of the signal does not resolve the problem of interpretation. We can read the signature of the ancient warming clearly, and we interpret it as natural because that interpretation fits the evidence and requires no additional assumptions. An artificial signature, if it existed, would present the same interpretive challenge in reverse. We would read it, and unless it carried unmistakable marks of artificiality, we would most likely interpret it as natural for the same reason. The default assumption, in the absence of strong evidence to the contrary, is that a disturbance in the carbon cycle has a natural cause. This default is reasonable and almost certainly correct for the events we actually observe in the record. But it also means that an artificial event lacking distinctive markers could be hiding in plain sight, recorded accurately but interpreted conventionally, its true nature invisible, not because the signal is absent, but because we have no reason to read it any other way. This is the deep lesson of the ancient warming event for the Silurian hypothesis. It shows that the record can preserve the signature of a rapid carbon-driven disturbance across tens of millions of years. It shows that such a signature would look much like what an industrial civilization would produce, and it shows that distinguishing artificial from natural causes on the basis of the carbon signal alone is beyond our current ability. To make such a distinction, we would need to find accompanying signals that natural processes cannot easily produce, signals that point specifically to technology rather than to ordinary geology. The question then becomes what those distinctively artificial signals might be and whether they would survive long enough to be found. The carbon signature is the starting point, the most likely thing to be detected, but it is also the most ambiguous. To move from ambiguity towards something more definitive, we have to consider the specific ways in which industrial activity changes the chemistry of carbon and what unique marks that process might leave behind. The act of burning buried carbon changes the atmosphere in ways that go beyond simply adding more of it, and understanding these changes in detail reveals why fossil fuel combustion leaves such a distinctive signature. When coal, oil, or natural gas is burned, The carbon that has been locked underground for millions of years is suddenly released into the atmosphere as carbon dioxide. This carbon, as discussed, carries the lighter isotopic signature characteristic of material that was once living, because it derives from ancient organisms. Releasing it rapidly dilutes the atmosphere's carbon with this lighter form, shifting the overall ratio. But there is an additional dimension to this signature that makes it even more distinctive, one that concerns not just the isotopes that reflect biological origin, but a specific isotope that reflects age. Carbon has a third isotope, a radioactive form that is continuously produced in the upper atmosphere by cosmic rays striking nitrogen. This radioactive carbon is present in living organisms because they continuously exchange carbon with their environment while alive. But once an organism dies and stops taking in new carbon, the radioactive form begins to decay, decreasing steadily over time. After a long enough period, tens of thousands of years, essentially all of the radioactive carbon has decayed away. Fossil fuels, which formed from organisms that died millions of years ago, contain no detectable radioactive carbon at all because it has long since vanished. When these fuels are burned, the carbon dioxide released is entirely free of the radioactive form. This means that burning fossil fuels not only shifts the stable isotope ratio toward the lighter form, but also dilutes the atmosphere's radioactive carbon with carbon that has none. This dilution effect is a recognized and measurable consequence of industrial activity in the present day. The proportion of radioactive carbon in the atmosphere has been altered by the addition of fossil carbon, and this change is recorded in materials forming during the industrial period. In principle, it represents a distinctive signature of fossil fuel combustion because few natural processes would dilute atmospheric radioactive carbon in this particular way. The problem, for the purpose of detecting an ancient civilization, is that the radioactive form of carbon decays completely within a span of tens of thousands of years. Any signature based on it would vanish long before the millions of years relevant to the Silurian hypothesis had passed. The radioactive carbon signature is useful for studying recent activity, but useless for detecting activity in the deep past because the signal itself does not survive. The stable isotope shift, however, does survive, and it remains the most durable carbon-based signature of fossil fuel combustion. The relative proportions of the lighter and heavier stable isotopes of carbon, once locked into sediment, persist across geological time. A rapid shift toward the lighter form, recorded in a thin interval of sediment, would be the lasting chemical trace of a large-scale release of fossil carbon. This is the signature that links the present to the ancient warming event discussed earlier, and it is the signature most likely to mark an industrial period in the deep record. But as established, this signature is ambiguous because natural carbon releases can produce similar shifts. The distinctiveness lies not in the shift itself, but in its characteristics, particularly its rate and its association with other signals. The rate of release is potentially the most diagnostic feature, and it deserves close attention. Natural carbon releases, even dramatic ones, tend to occur over spans of thousands of years or longer, because the natural processes that release carbon operate relatively slowly. Volcanic activity releases carbon gradually over extended periods. The destabilization of carbon-rich deposits, while capable of releasing large amounts, also tends to unfold over millennia. An industrial civilization, by contrast, can release carbon extraordinarily quickly, burning through deposits that took millions of years to form in a matter of centuries. This rate, the speed at which the carbon enters the system, is the feature that most distinguishes industrial combustion from natural release. A signature showing an exceptionally rapid injection of light carbon, faster than any known natural process could achieve, would be a strong indication of an artificial cause. The difficulty, as noted, is resolving the rate from the record across deep time. The faster an event occurs, the harder it is to capture in the slowly accumulating sediments of the distant past. An event lasting only a few centuries might be compressed into a layer too thin to distinguish from an instantaneous event, or, conversely, blurred together with the surrounding centuries so that it appears more gradual than it was. The precision required to determine that a carbon release occurred over centuries rather than millennia is generally beyond what the deep record can provide, especially for events tens of millions of years old. This means that even the most diagnostic feature of an industrial carbon signature, its rapidity, might be unrecoverable from the ancient record, leaving us unable to distinguish it from a slower natural release on the basis of rate alone. There is, however, a further consideration that adds nuance to this picture. The total amount of carbon released combined with the duration of the release determines not just the magnitude of the isotopic shift, but also the pattern of recovery afterward. The way the carbon system returns to balance after a disturbance carries information about the nature of the disturbance. A very rapid release, followed by a particular pattern of drawdown, might leave a recovery signature subtly different from that of a slower release. Scientists studying ancient carbon cycle disturbances examine not just the onset of the shift, but its full shape over time, the rise and the subsequent decline, and this fuller picture can constrain the possible causes. Whether such analysis could ever distinguish an artificial release from a natural one, with confidence remains uncertain, but it represents a possible avenue, one that depends on the quality and resolution of the available record. Beyond carbon itself, the combustion of fossil fuels produces other byproducts that enter the environment and could leave traces. The burning of coal, in particular, releases a range of substances, including trace metals and particles that settle out of the atmosphere and into sediments. Some of these substances are present in fossil fuels in concentrations higher than in the surrounding environment, and their release could create localized or even widespread enrichments in the sediments forming during the period of combustion. Certain metals associated with industrial activity, if found in anomalous concentrations in a thin interval of ancient sediment, could constitute a supporting signal alongside the carbon shift. The challenge, again, is that many of these substances also have natural sources, and distinguishing an industrial enrichment from a natural one requires careful analysis and, ideally, the coincidence of multiple anomalies that together resist natural explanation. The combustion signature, then, is a composite. It consists of a carbon isotope shift, which is durable but ambiguous, a radioactive carbon dilution, which is distinctive but short-lived, a potential rate signature, which is diagnostic but hard to recover, and various chemical byproducts, which are supporting but individually inconclusive. No single element of this composite is sufficient to identify an industrial civilization with confidence across deep time. But the combination, if it could be found and resolved, would be more compelling than any part alone. This is the recurring theme of the entire inquiry. Individual signals are ambiguous or fragile, but the coincidence of multiple independent signals, each pointing in the same direction, would be far harder to explain away. The search for an ancient civilization, if pursued seriously, would be a search for such coincidences, for clusters of anomalies that natural processes would be unlikely to produce together. This focus on combustion reflects an assumption worth examining, namely that an industrial civilization would necessarily burn buried carbon. Human industrial society has been built on fossil fuels, and our most prominent planetary signature derives from that fact. But a different civilization might have developed along a different path, drawing its energy from sources that leave no carbon signature at all. A civilization powered by other means might never produce the carbon shift that we treat as the primary marker, leaving us to search for a signature that was never created. This possibility widens the problem considerably, because it means that the absence of a carbon signature would not even rule out a civilization. It would only rule out a civilization that burned carbon the way we have. The space of possible civilizations is larger than the space of signatures we know how to look for, and this mismatch is one of the deepest challenges in the entire endeavor. Yet even setting aside these alternative paths and focusing only on a civilization resembling our own, the combustion signature alone would not be enough to convince us. We would want corroborating evidence, signals of a different kind that point unambiguously toward technology rather than chemistry. Among the candidates for such evidence, one class stands out for its potential durability and its unusual nature, The materials that a civilization manufactures, particularly the synthetic substances that do not occur in nature at all, might form a signature unlike anything the planet has produced before. These materials, foreign to the natural world and resistant to the processes that break down living matter, could persist in ways that organic remains cannot, creating a layer in the record that would be genuinely without precedent. The nature and durability of these manufactured materials is the next thread to follow. Among all the materials a civilization produces, the synthetic substances that do not exist in nature occupy a special category, because their very presence in the record would signal something that ordinary geology cannot create. Plastics are the foremost example. These materials are manufactured from carbon-based compounds, assembled into long molecular chains that do not occur naturally, and that the organisms and processes of the natural world are poorly equipped to break down. Humanity has produced plastics in staggering quantities, billions of tons over a span of decades, and a large fraction of that material persists in the environment, accumulating in landfills, soils, rivers, and oceans. The durability that makes plastic useful, its resistance to decay, also makes it a candidate for long-term preservation in the geological record, potentially forming a layer marked by the presence of a substance the planet had never seen before. To understand why plastic is so unusual as a potential signature, it helps to consider how it behaves over time compared to natural materials. Organic matter, the stuff of living things, is readily broken down by bacteria, fungi, and chemical processes, recycled back into the environment within timescales ranging from days to, at most, a few thousand years under exceptional preservation. Plastic resists this breakdown. The microorganisms that decompose natural organic matter have not evolved efficient means to digest synthetic polymers, because these materials are evolutionarily novel, having existed for only a few decades. As a result, plastic persists far longer than natural organic material would, and while it does eventually break down under the influence of sunlight, heat, and mechanical action, this breakdown often produces smaller and smaller fragments rather than fully decomposing the material. These fragments, tiny particles of plastic, spread throughout the environment and settle into sediments where they could become incorporated into the rock record. The question of whether plastic would survive across millions of years is genuinely open and depends on processes that are not fully understood, because plastic has not existed long enough for us to observe its ultimate fate. On one hand, the chemical stability that makes plastic resistant to decay suggests it could persist for a very long time, especially if buried quickly in conditions that protect it from sunlight and oxygen. Buried in sediment, away from the agents that degrade it at the surface, plastic might endure long enough to be incorporated into forming rock. On the other hand, the heat and pressure of deep burial over geological spans would likely transform plastic chemically, breaking down its molecular structure and altering it into something else. Whether the end product would retain any recognizable signature of its synthetic origin is uncertain. It might leave a distinctive chemical trace, an anomaly in the composition of the sediment, even if the original material were transformed beyond recognition as plastic. This uncertainty itself is significant for the Silurian hypothesis. If we cannot be sure that the plastic we are producing now would leave a recognizable trace in the deep future, then we cannot be sure that an ancient civilization producing similar materials would have left a trace we could find today. The very novelty of plastic, which makes it such a distinctive marker in the present, becomes a liability when projected across deep time, because we lack the experience to know how it would fare. What we can say is that the production of synthetic materials represents a kind of activity that natural processes do not replicate. If a recognizable trace of such materials were found in ancient sediment, it would be difficult to explain by natural means, making it a potentially powerful signature, more distinctive in its way than the ambiguous carbon shift. The breakdown products of plastic deserve particular attention, because even if the original material does not survive, what it becomes might. As plastic fragments and degrades, it releases various compounds, and these could enter the sediment and persist. Some of the chemical components of plastics and their additives are themselves unusual, not found in natural systems, and their presence in ancient sediment could serve as a marker. The study of how these compounds behave over long timescales is in its infancy, precisely because the materials are so new, but the principle is clear. A civilization that manufactures novel chemicals introduces those chemicals into the environment, and some fraction of them, or their breakdown products, might persist in forms that natural processes would not produce. The search for such persistent novel compounds is one of the more promising directions for identifying an industrial signature, because it targets exactly the kind of substance that distinguishes manufacturing from natural chemistry. It is worth placing the scale of plastic production in perspective, because the sheer quantity is part of what makes it a plausible global signature. The amount of plastic humanity has produced is enormous, and it continues to grow. This material does not stay in one place. It is transported by rivers to the oceans, where it accumulates and breaks into fragments that spread across vast areas, including the deep sea floor, one of the more stable and preservation-friendly environments on the planet. Plastic particles have been found in remote locations far from any source, carried by wind and water across the globe. This widespread distribution means that the plastic signature, like the carbon signature, is not confined to vulnerable local sites, but is being deposited across many environments simultaneously, improving its chances of being preserved somewhere. The global reach of the material is what gives it potential as a planetary marker rather than a merely local curiosity. The comparison between plastic and natural materials in the record highlights how unusual a synthetic layer would be. Throughout the planet's history, the materials deposited in sediments have been those produced by natural processes, minerals, organic matter, the remains of organisms, particles from erosion, and volcanic activity. A layer containing abundant synthetic polymers, or their distinctive breakdown products, would be a departure from everything that came before, a band in the record marked by the presence of substances that geology alone cannot make. Future geologists examining such a layer, if it survived, would encounter something genuinely anomalous, a signature that demanded explanation and that natural processes could not readily provide. This is what gives the plastic signature its potential power. It is not an amplification of a natural pattern, like the carbon shift, but the introduction of something categorically new. Yet, the same caution that applies throughout the inquiry applies here. The survival of such a layer across millions of years is uncertain, dependent on burial conditions and on the chemical fate of the materials under heat and pressure. A layer that exists clearly now might be transformed or destroyed over deep time, leaving only a faint and ambiguous chemical residue, or nothing at all. And even if a residue survived, recognizing it as the product of manufacturing rather than some unusual natural process would require understanding its composition in detail and ruling out natural explanations. The plastic signature, like the others, is most powerful not in isolation, but as one element in a coincidence of signals. A novel chemical residue found alongside a rapid carbon shift, alongside other anomalies, would together build a case that no single signal could make alone. There is also a sobering reflection embedded in the plastic signature, one that connects the deep past to the present and future. The material we are producing now in such vast quantities is creating a layer in the record that will mark our period for whatever future investigators might one day read it. We are, in effect, writing our own signature into the planet, a signature whose ultimate legibility we cannot predict. If our plastic persists in recognizable form, it will be one of the clearest marks of our existence. If it transforms and fades, it will join the long list of evidence that the planet quietly erases. Either way, the act of considering plastic as a potential ancient signature forces us to confront the impermanence of even our most durable products, and to recognize that the question we ask about hypothetical ancient civilizations is the same question that the deep future will ask about us. This brings the inquiry to a different class of signature altogether, one that does not depend on the survival of manufactured objects or the persistence of synthetic chemicals, but on something more fundamental and, in some respects, more distinctive. The activity of a civilization can leave marks at the atomic level, marks produced by processes that occur nowhere in nature except under extraordinary circumstances. These atomic signatures, scattered across the entire globe by certain kinds of technological activity, represent perhaps the most unambiguous fingerprint a civilization could leave, a signal that natural geology has no way to counterfeit. Understanding these signatures and whether they could survive the journey through deep time is the next and perhaps most striking piece of the puzzle. The detonation of nuclear weapons released into the global environment, something that natural processes do not produce in any comparable way, and this fact creates one of the most distinctive markers a civilization could leave. When atomic devices were tested in the atmosphere during the middle of the 20th century, the reactions they triggered generated a range of artificial isotopes, forms of various elements that are either entirely absent in nature or present only in vanishingly small quantities. These isotopes were lofted high into the atmosphere and then distributed across the entire planet, settling out and becoming incorporated into soils, sediments, ice, and living tissues everywhere. The result was a thin, globally synchronous layer marked by the presence of substances that had not existed in the environment before, a signature written simultaneously across the whole surface of the world. This global layer is so distinctive and so precisely datable that it has been proposed as a marker for the boundary of a new geological interval. Its appearance is sharp, corresponding to the brief period of intensive atmospheric testing, and its distribution is worldwide, making it one of the cleanest stratigraphic markers ever created. The isotopes involved are products of nuclear reactions, and their presence in the environment, beyond trace natural backgrounds, points unambiguously to technological activity capable of splitting or fusing atomic nuclei on a significant scale. No natural geological process produces these particular isotopes in these quantities and distributes them globally in a single thin layer. In this sense, the nuclear signature is qualitatively different from the carbon shift or even the plastic layer. It is not an amplification of a natural pattern, nor a novel chemical that natural processes merely fail to make. It is the direct product of a kind of physics that, on Earth, occurs naturally only under the rarest circumstances. The strength of this signature as a marker of technology is therefore considerable. If a future investigator or an investigator looking into the deep past found a thin global layer enriched in artificial isotopes produced by nuclear reactions, the natural explanations would be few and would themselves be remarkable. This makes the nuclear signature, in principle, one of the most diagnostic fingerprints a civilization could leave, a signal that points clearly toward technology rather than toward ambiguous natural disturbance. The problem, as with the radioactive carbon discussed earlier, lies in durability. Many of the isotopes produced by nuclear reactions are themselves radioactive and decay over time, transforming into other elements at characteristic rates. The question of whether a nuclear signature could survive across deep time depends entirely on the half-lives of the isotopes involved and on what they leave behind when they decay. Half-life is the term for the time it takes for half of a quantity of a radioactive isotope to decay. Different isotopes have vastly different half-lives, ranging from fractions of a second to billions of years. The isotopes produced by nuclear weapons span a wide range. Some decay within days or years, vanishing almost immediately on geological timescales. Others persist for decades or centuries, long enough to mark a recent event, but not nearly long enough to survive millions of years. A few have half-lives long enough to remain detectable across the spans relevant to the Silurian hypothesis, and these are the ones that matter for the question of detecting an ancient civilization. The signature that survives is not the full suite of isotopes present at the moment of the event, but only the subset stable enough or long lived enough to endure, along with the stable products into which the others decay. This decay process actually creates a subtle complication and a subtle opportunity. As radioactive isotopes decay, they transform into specific daughter products, often stable isotopes of other elements. An unusual abundance of a particular daughter isotope, in a ratio that differs from what natural processes produce, could itself be a signature, a lingering trace of the radioactive parent that has long since vanished. In this way, even after the original artificial isotopes have decayed away, their former presence might be inferred from the anomalous abundance of their decay products, provided those products are themselves distinctive and stable. This extends the potential lifetime of a nuclear signature beyond the lifetimes of the original isotopes, though it requires that the decay products be measurable and distinguishable from natural backgrounds, which is not always the case. There's another way that a nuclear signature might persist, one that does not depend on weapons testing at all, but on the broader use of nuclear technology. A civilization that harnessed nuclear reactions for energy would process certain elements in ways that alter their isotopic composition, concentrating particular isotopes and depleting others. These alterations could leave traces in the materials a civilization handled, and under the right circumstances, such altered isotopic ratios might survive in the environment. Remarkably, there's a natural precedent for this. At one location on Earth, deep in the geological past, a deposit of uranium became concentrated enough and was configured in such a way that a natural nuclear reaction sustained itself for an extended period, hundreds of thousands of years, billions of years ago. This natural reactor left detectable isotopic anomalies in the surrounding rock, anomalies that scientists discovered and recognized as the products of nuclear reactions. The fact that such a signature survived for billions of years demonstrates that nuclear processes can leave durable isotopic marks, provided the conditions preserve them. This natural reactor is a powerful illustration for the Silurian hypothesis because it proves that the isotopic signature of nuclear activity can persist across the deepest spans of geological time. If a natural reaction billions of years ago left a detectable trace, then a civilization using nuclear technology might leave a similar trace in the form of altered isotopic ratios in the materials it processed and in the environment those materials entered. The challenge is that such a signature would be localized, confined to the specific places where the civilization conducted its nuclear activities, rather than spread globally like the fallout from atmospheric testing. A localized signature is harder to find because it requires sampling the right location, whereas a global signature is recorded everywhere. The fallout signature is global but short-lived, while the processing signature is durable but local. Neither is ideal, and detecting either across deep time would require both luck and a reason to look. The discovery of the natural reactor itself offers a lesson in how such signatures come to light. It was found not because anyone was searching for ancient nuclear activity, but because careful measurements of isotopic ratios in uranium or revealed an anomaly, a depletion of a particular isotope that should not have occurred naturally unless something had consumed it. Scientists confronted with this anomaly worked out that a natural reaction must have taken place, and subsequent investigation confirmed it. This is instructive because it shows that distinctive isotopic signatures, when they survive, can be recognized for what they are, but only when someone measures the right thing and notices the discrepancy. An artificial signature in the deep record might similarly reveal itself as an anomaly in isotopic ratios, but only if it were measured and only if the anomaly were large enough and distinctive enough to demand explanation. The nuclear signature, then, presents a paradox that runs through the entire inquiry. It is among the most diagnostic signatures a civilization could leave, pointing unambiguously to technology in a way that few other signals can match. Yet its most distinctive components are also among the most ephemeral, decaying away within timescales far shorter than those the question demands. What survives across deep time is a residue, an altered isotopic ratio, a depletion or enrichment that must be measured precisely and recognized as anomalous. Such residues can survive, as the natural reactor proves, but finding them requires sampling the right material and asking the right question. The signature exists, in principle, but its detection across millions or tens of millions of years would depend on a chain of fortunate circumstances, each unlikely on its own. These considerations taken together with the carbon and plastic signatures, begin to assemble a fuller picture of what an industrial civilization might leave behind and how its various marks would fare across deep time. Each signature has its strengths and weaknesses, its durability and its ambiguity, its global reach or its local confinement. None alone is conclusive. But the consideration of these signatures also raises a question about our own period specifically, about whether the marks we are currently making are significant enough to constitute a recognizable break in the planet's history, a new chapter distinct from everything before. This question has become the subject of serious scientific debate, and examining it reveals how scientists are thinking in real time about the very kind of signature the Silurian hypothesis concerns, applied not to a hypothetical ancient civilization, but to ourselves. Scientists have been debating with considerable seriousness whether human activity has pushed the planet into a new geological interval, one defined by our own influence on the Earth's systems. The geological timescale divides the planet's history into named intervals of various lengths, each defined by distinctive features in the rock record that mark transitions in conditions, in life, or in the chemistry of the planet. These divisions are not arbitrary. They correspond to real and recognizable changes preserved in the sediments, changes significant enough and widespread enough to serve as boundaries. The proposal that we have entered a new interval defined by human activity rests on the claim that our influence has become significant enough to leave just such a boundary in the record, a marker that future investigators could identify as the start of a distinct period. The case for this proposal draws directly on the kinds of signatures we have been examining. Human activity has shifted the carbon isotope balance of the atmosphere through fossil fuel combustion. It has scattered artificial isotopes across the globe through nuclear testing. It has produced synthetic materials in quantities that are accumulating in sediments worldwide. It has altered the nitrogen cycle through industrial agriculture. It has accelerated erosion and sediment movement through construction and land use. It has driven changes in the distribution and abundance of species, including extinctions and the global spread of certain organisms. Each of these represents a measurable change in the planetary system, and each is being recorded to some degree in the sediments forming today. The argument is that these changes, taken together, constitute a signature distinct enough to mark a new chapter in the planet's history. The debate over this proposal is instructive precisely because it concerns the same questions the Silurian hypothesis raises, but applied to the present rather than to a hypothetical past. Scientists arguing about whether human activity has created a new geological interval are, in effect, asking what signature we are leaving and whether it is significant and durable enough to register as a boundary. This is the forward-looking version of the backward-looking question the Silurian hypothesis poses. By examining how scientists evaluate our own signature, we gain insight into how an ancient signature would have to appear in order to be recognized, and into the criteria by which such a signature would be judged. The exercise of defining our own mark on the planet is, in a sense, a rehearsal for the exercise of detecting the mark of another civilization in the deep past. One of the central difficulties in the debate concerns where precisely to place the boundary of the proposed new interval. A geological boundary must be marked by a specific, identifiable signal in the rock record, ideally one that is sharp, global, and synchronous, so that it can be recognized consistently in sediments around the world. Various candidates have been proposed for this marker. The appearance of artificial isotopes from nuclear testing offers a sharp and globally synchronous signal, recorded almost simultaneously everywhere, which makes it attractive as a boundary marker. Other candidates include the first appearance of synthetic materials, shifts in the carbon record, and changes in the assemblages of organisms preserved. The choice of marker matters because it determines exactly when the new interval is said to begin, and different markers point to different starting points, from the beginnings of agriculture thousands of years ago to the industrial period of recent centuries to the middle of the 20th century. This question of timing illuminates an important aspect of how signatures work. A signature is not simply present or absent. It has an onset, a magnitude, and a character that determine how clearly it marks a transition. A gradual change spread over thousands of years makes a poor boundary because it is hard to pin to a specific point. A sharp change concentrated in a brief interval makes a much better boundary because it appears as a distinct line in the record. This is why the nuclear signature is favored by many as a boundary marker, despite its short-lived components, because its onset is so abrupt and so globally synchronized. For the Silurian hypothesis, this suggests that an ancient civilization's signature would be most recognizable if it included some sharp, globally synchronous element, rather than only gradual changes that would blur into the surrounding record and resist identification as a distinct event. The debate also highlights the distinction between the immediate visibility of a signature and its long-term preservation. The signatures of human activity are clearly visible now in the sediments forming in the present, because we can measure them directly and in detail. But the question of whether these signatures will persist across deep time is separate and more uncertain. Some, like the stable carbon isotope shift, are likely to endure. Others, like the artificial isotopes from nuclear testing, will largely decay away, leaving only residues. Still others, like synthetic materials, have an uncertain fate. The signature that is obvious to us now, examining freshly formed sediments, is not necessarily the signature that would survive to be read by a distant future investigator. This temporal dimension is crucial. The proposal for a new geological interval concerns what we are recording now, but the Silurian hypothesis concerns what survives across millions of years, and the two are not the same. There is a further subtlety in the debate that bears on the question of detection. For a signature to define a geological boundary, it must not only be present and durable, but also distinguishable from natural variation. The geological record contains many natural fluctuations in carbon, in sediment, in species, and a human signature must stand out against this natural background to be recognized as something different. Part of the argument for a new interval is that the human signature is not merely a fluctuation within the normal range, but a departure from it, a change in kind as well as in degree. The introduction of entirely synthetic materials and artificial isotopes is a change in kind because these things did not exist before. The acceleration of changes beyond natural rates is a change in degree extreme enough to be notable. The combination is what makes the case that the human signature is genuinely distinct, and the same logic would apply to detecting an ancient civilization. Its signature would have to stand out against natural variation, either in kind or in degree, to be recognized. The discussion among scientists about our own period reveals how carefully such judgments must be made and how much depends on the choice of criteria. Reasonable experts disagree about whether the human signature yet rises to the level of a formal geological boundary, about which marker best defines it, and about when it should be said to begin. These disagreements are not failures of science, but reflections of the genuine complexity of reading and defining signatures in the planetary record. They demonstrate that even for a signature we can observe directly and in real time, the question of whether it constitutes a recognizable, durable, distinct mark is not simple. If it is this difficult for our own signature, observed as it forms, then it would be far more difficult for an ancient signature, observed only as a faint residue across tens of millions of years of subsequent alteration. This is perhaps the most valuable lesson the debate offers to the Silurian hypothesis. It shows that the recognition of a civilization's signature is not automatic, even under the most favorable conditions. It requires durable, distinct, globally distributed markers, a reason to look for them, and careful analysis to distinguish them from natural processes. Our own signature, with all these advantages, is still the subject of debate. An ancient signature, lacking the advantage of direct observation and degraded by deep time, would face every difficulty our signature faces and more. The debate over a new geological interval thus serves as a kind of measuring stick, calibrating just how demanding the detection of a civilization's signature truly is, and underscoring how easily such a signature could fall short of recognition. But all of this discussion of signatures and their preservation assumes that the record persists long enough to be read. There is a more fundamental force at work, one that does not merely fail to preserve evidence, but actively destroys it, and that operates relentlessly across the entire surface of the planet. Before we can fully assess what an ancient civilization might leave behind, we have to confront the processes that erase the record itself, the slow but unstoppable forces that wear away the land and carry it into the sea, dismantling the very archive in which any signature would have to be stored. These forces set the ultimate limit on how far back the record can reach, and understanding them reveals why the deep past grows so dark so quickly. The surface of the planet is constantly being worn away, and this relentless dismantling sets a hard limit on how long any record can survive in any given place. Erosion is the collective name for the processes that break down and remove material from the land. Water is the most powerful agent. Rain falls on high ground, gathers into streams and rivers, and carries away particles of rock and soil, transporting them downhill and ultimately toward the sea. Over time, this process can remove staggering amounts of material, carving valleys, lowering mountains, and stripping away entire landscapes. Wind contributes by lifting and carrying fine particles, scouring exposed surfaces. Ice, in the form of glaciers, grinds against the rock beneath it, plucking away fragments and bulldozing material across great distances. Even temperature changes and the chemical action of water contribute, cracking rock and dissolving it grain by grain. The cumulative effect of these processes is that the surface of the continents is in a constant state of removal. In regions of high elevation and steep terrain, erosion is rapid, stripping away meters of material over relatively short geological spans. In flatter, more stable regions, it is slower, but it never stops entirely. The consequence for the geological record is profound. Material laid down on the land is, in many places, eventually removed rather than preserved. A layer of sediment deposited today might be eroded away long before it has a chance to become rock and survive into the deep future. The land is not a reliable archive because the land itself is being dismantled. The very surfaces on which a civilization would live and build are among the surfaces most subject to erosion because they are elevated, exposed, and accessible to the agents of removal. This is why the survival of a record depends so heavily on burial in settings where material accumulates rather than being removed. The places where sediment piles up and is preserved are typically low-lying areas, basins where rivers deposit their loads, the floors of lakes, and especially the floors of seas and oceans. In these settings, material settles and accumulates layer upon layer, with a reasonable chance of being buried deeply enough to survive. But material does not simply travel from the eroding highlands to these preservation basins without consequence. In the process of transport, it is broken down, sorted, and mixed. A delicate object eroded from the land does not arrive intact at the sea floor. It is fragmented, abraded, and dispersed, its original form destroyed long before it reaches a place where it might be preserved. The journey from the eroding surface to the preserving basin is itself a process of destruction, ensuring that what arrives is rarely more than scattered particles. For the question of detecting a civilization, this has stark implications. The objects and structures of a civilization located on the land are subject to erosion and would be broken down and removed over geological time. Their fragments might be transported to depositional basins, but only as unrecognizable particles, mixed with the vast quantities of natural sediment. The chemical signatures, being dispersed globally through the atmosphere and ocean, have a better chance because they are deposited directly into the preserving basins along with everything else, rather than having to survive transport from the land. This reinforces, once again, the conclusion that chemical signatures are more likely to survive than physical objects. The objects are on the eroding land. The chemical signals are in the global system, settling into the preserving depths. Erosion destroys the former while merely diluting the latter. The rates of erosion vary enormously depending on the setting, and this variation matters for understanding how far back the record can reach. In tectonically active regions where the land is being pushed upward, erosion is rapid because the rising land provides the elevation that drives the removal of material. Mountain ranges, for all their apparent permanence, are among the most rapidly eroding features on the planet, worn down even as they rise. In stable interior regions of continents, erosion is slower and ancient surfaces can survive longer. But even in the most stable regions, the timescales over which surfaces survive are limited compared to the age of the planet. Very ancient land surfaces, preserved more or less intact from the deep past, are rare and exceptional. Most of the land surface we see today is geologically young, having been shaped and reshaped by erosion over spans far shorter than the planet's history. This explains a crucial feature of the geological record, namely that it grows dramatically sparser the further back one looks. The record of recent geological time is relatively rich, because little erosion has yet had the chance to remove it. The record of the deep past is far thinner, because it has been subjected to hundreds of millions of years of erosion, removal, and destruction. Each passing era erases some of what came before, so that the oldest records are the most degraded and the most incomplete. This decay of the record with age means that the deeper one searches into the past, the less there is to find, and the harder it becomes to detect any signal, natural or artificial. An ancient civilization, located far back in time, would have its signature subjected to the full weight of this accumulated erosion, with each subsequent era removing more of whatever remained. There is a particular consequence of erosion that deserves emphasis, concerning the relationship between time and exposure. The rock that we can actually examine at the surface today is rock that has been exposed by erosion, brought to the surface from below as the material above it was stripped away. This means that the very process that destroys the record is also the process that reveals it. We see ancient rock precisely because erosion has removed everything that lay above it. But this creates a selection effect. The ancient rock we can see is the rock that has survived erosion and been exposed, while vast quantities of ancient rock have been entirely removed and are simply gone. We are sampling the survivors, not the full record, and the survivors are a biased and incomplete subset. An ancient civilization's signature, if it existed, would have to be in one of these surviving exposed remnants for us to find it, and the chance of that is reduced by every era of erosion that is passed. The transport of eroded material to the oceans also connects to a deeper process that goes beyond mere removal, one that involves the recycling of the planet's surface itself. The sediment that accumulates on the ocean floor does not simply rest there indefinitely. Over very long timescales, the floor of the ocean is itself drawn into the interior of the planet by the slow movement of the rigid plates that make up the outer shell of the Earth. This process carries the accumulated sediments, along with any signatures they contain, down into the depths where they are subjected to extreme heat and pressure, melted and ultimately recycled. This means that even the preservation basins, the places where material accumulates and survives longest, are not permanent. They too are eventually consumed on timescales of a few 100 million years by the larger machinery of the planet's geology. The ocean floor, the best archive of all, has a limited lifespan before it is destroyed entirely. This recycling of the ocean floor places an outer limit on how far back the marine record can reach, and it is a limit far shorter than the age of the planet. The oldest ocean floor existing today is only a fraction of the planet's age, because older ocean floor has already been recycled into the interior. This means that the marine sedimentary record, the best and most complete archive of the planet's chemical history, does not extend back through the whole of geological time. For the deeper past, we are left with only the fragments preserved on the continents, which are sparser, more disturbed, and more heavily eroded. The combination of erosion on land and recycling of the ocean floor means that the record available for the deep past is doubly limited, degraded on the continents and absent from the oceans beyond a certain age. These forces of erosion and recycling are the ultimate reason the deep past is so difficult to read, and they bring the inquiry to the most fundamental process of all, the one that does not merely wear away the surface, but consumes the very fabric of the record and returns it to the interior of the planet. The slow movement of the plates, which carries the ocean floor down into the depths, is part of a vast cycle that continuously creates and destroys the surface of the Earth. Understanding this cycle and how it sets the absolute limit on the survival of any ancient record reveals why the question the Silurian hypothesis poses can never be fully resolved, and why the deep past must remain, to a significant degree, beyond our reach. The outer shell of the Earth is not a single solid layer, but is broken into large rigid pieces that move slowly over the hotter, deformable material beneath them. These pieces, the tectonic plates, drift across the surface of the planet at rates comparable to the growth of fingernails, a few centimeters per year. But over geological time, this slow motion accomplishes enormous transformations. The plates carry the continents and the ocean floors with them, colliding, separating, and sliding past one another. Where plates move apart, new material rises from below to fill the gap, creating fresh ocean floor. Where plates come together, one is often forced beneath the other, descending into the hot interior of the planet in a process that consumes the surface material and recycles it. This cycle of creation and destruction is the engine that shapes the planet's surface over the longest timescales, and it is the ultimate destroyer of the geological record. The process by which one plate descends beneath another is the key to understanding why the deep record is limited. As a plate-carrying ocean floor is driven downward into the interior, it takes with it everything that lies upon it, including the accumulated sediments that record the planet's chemical history. These sediments, descending into regions of intense heat and pressure, are transformed beyond recognition. The minerals recrystallize, the chemical signatures are altered or destroyed, and the material is ultimately melted and incorporated into the planet's interior, some of it eventually returning to the surface through volcanic activity in an entirely transformed state. Whatever record those sediments contained, whether natural or artificial, is erased completely in this process. The descent into the interior is not preservation, but obliteration, the most thorough destruction of evidence that the planet is capable of. This process explains why the ocean floor, despite being the best archive of the planet's chemical history, does not preserve a record extending back through the whole of geological time. Ocean floor is continuously created where plates separate and continuously consumed where they descend. The result is that ocean floor has a limited lifespan, existing for at most a few 100 million years before being recycled. There is no ocean floor on the planet today that dates back to the deep past because all of the older ocean floor has already been consumed and replaced. The marine record, which preserves chemical signatures so well within its limited lifespan, simply does not exist for the deeper past, having been recycled into the interior long ago. For the periods most relevant to a hypothetical ancient civilization deep in time, the marine archive is largely gone, destroyed by the very process that continuously renews the planet's surface. This is a profound limitation because the marine record is precisely the kind of archive in which a civilization's chemical signature would be best preserved. The deep ocean floor accumulates sediment steadily in conditions favorable to preservation, recording global chemical signals from across the planet. If a civilization's carbon shift or its other chemical signatures were to survive anywhere, the deep ocean floor would be among the most promising places. But that archive is repeatedly destroyed, recycled into the interior on timescales of a few 100 million years. A civilization existing further back than that would have had its best potential archive consumed entirely, leaving only the continental record, which is sparser, more disturbed, and more heavily eroded. The recycling of the ocean floor thus removes the most favorable archive precisely for the deepest and most interesting parts of the past. The continents fare somewhat better because they are made of lighter material that resists being drawn into the interior, and so they persist far longer than ocean floor. Some continental rock is genuinely ancient, dating back billions of years, and these ancient remnants preserve glimpses of the deep past that the oceans cannot. But the continents are not immune to destruction. They are subjected to the relentless erosion discussed earlier, worn down and reshaped over time. They are also caught up in the collisions of plates, folded, faulted, heated, and deformed. as continents collide and mountain ranges rise. This deformation alters the rock, distorting and often destroying the delicate signatures it might have contained. The ancient continental record that survives is therefore not pristine. It has been heated, compressed, folded, and chemically altered, its original signals degraded by the violence of the processes that preserved it. Reading such altered rock is possible but difficult, and the finer signals, the subtle chemical anomalies that might indicate a civilization, are precisely the ones most likely to be lost in the alteration. The combination of these processes, erosion stripping the land, recycling consuming the ocean floor, and deformation altering the surviving continental rock, means that the record available for the deep past is fragmentary in the extreme. The further back one looks, the less survives, the more it has been altered, and the harder it becomes to extract any reliable signal. This decay of the record with time is not a minor inconvenience, but a fundamental feature of how the planet works. The Earth is a dynamic body that continuously remakes its own surface, and in doing so, it continuously destroys the record of its own past. The planet is, in a sense, perpetually erasing its own history, retaining only fragments and rewriting the rest. This is why the deep past grows dark so quickly, and why the question of what it might contain can never be answered with certainty. For the Silurian hypothesis, this sets the ultimate boundary on what is knowable. A civilization existing within the last few 100 million years might have left signatures in marine sediments that, in principle, could still survive, though they would be subtle and difficult to find. A civilization existing further back than that would have had its marine record entirely recycled, leaving only the degraded continental record where the chance of finding and recognizing a signature drops toward the negligible. The deeper into the past one pushes, the more thoroughly the evidence has been destroyed, until at a certain point, the record simply cannot answer the question at all. The planet's own geological activity has erased whatever there was to find, and no amount of searching can recover what has been melted into the interior and recycled. This understanding reframes the entire question in an important way. The Silurian hypothesis is often received as a provocative suggestion that there might have been ancient civilizations on Earth, but its deeper and more rigorous content is a statement about the limits of knowledge. It establishes that, beyond a certain point in the past, the record is simply insufficient to detect a civilization, even if one existed, because the processes that destroy the record operate faster than the signatures can survive. This is not a claim that civilizations existed. It is a demonstration that their absence from the record cannot be taken as proof of their non-existence, because the record itself is incapable of preserving the evidence across such spans. The silence of the deep past is, at least in part, a silence imposed by the planet's own destruction of its history, not necessarily a silence reflecting an empty past. This distinction between a genuine absence and an absence that merely reflects the limits of detection is one of the most important ideas in the entire inquiry, and it has implications that extend far beyond the question of ancient civilizations on Earth. It is a problem of logic and evidence that applies wherever we search for traces of the past or of life elsewhere. The failure to find evidence can mean that there is nothing to find, or it can mean that the evidence has been destroyed or never preserved, or lies beyond our ability to detect. Distinguishing among these possibilities is often impossible, and treating the failure to find evidence as proof of absence is a logical error with serious consequences. This error, and the careful reasoning required to avoid it, lies at the heart of how we should interpret the silence we encounter, both in the deep past of our own planet and in the vast reaches of the universe beyond. The failure to find evidence of something is not the same as evidence that the something never existed, and this distinction, though it sounds like a simple matter of logic, has consequences that reach into the deepest questions we can ask about the past and about life beyond our world. When we search the geological record and find no clear sign of an ancient civilization, there are several possible explanations for that absence, and they are not equivalent. It might be that no civilization ever existed, and so there was never anything to find. It might be that a civilization existed but left signatures too faint to detect. It might be that signatures were left but have since been destroyed by erosion, recycling, and alteration. Or it might be that signatures survive but we have not looked in the right place or measured the right thing. The empty result is consistent with all of these, and on its own, it cannot tell us which is true. This is the problem that the Silurian hypothesis ultimately illuminates. Throughout the inquiry, we have seen how thoroughly the record destroys evidence, how unlikely preservation is, how ambiguous even surviving signatures would be, and how the deep past grows progressively darker as the record decays. The cumulative effect of these limitations is that the absence of evidence in the deep record carries very little weight as proof that nothing existed. The record is simply too incomplete, too biased, and too degraded to support such a strong conclusion. We cannot say that the deep past contained no civilization. We can only say that we have found no evidence of one, which is a far weaker statement, because the record is incapable of preserving such evidence reliably across the relevant spans of time. The silence is real, but its meaning is ambiguous. It is essential to be clear about what this does and does not imply, because the reasoning is easily misunderstood. The Silurian hypothesis does not claim that an ancient civilization existed, nor does it provide any evidence that one did. There is no positive indication of any such thing in the record. Every anomaly we observe in the deep past is adequately explained by natural processes, and there is no need to invoke a civilization to account for anything we have found. The hypothesis is not an argument for the existence of ancient civilizations. It is an argument about the limits of what we can rule out. It establishes that we cannot use the absence of evidence to confidently exclude the possibility, because the record could not preserve the evidence even if there were something to preserve. This is a statement of humility about the limits of knowledge, not a claim about what the past contained. This kind of reasoning, the careful distinction between absence of evidence and evidence of absence, is fundamental to good science, and it applies far beyond the specific question of ancient civilizations. Whenever we search for something and fail to find it, we must ask whether our search was capable of detecting it had it been there. If the search was thorough and sensitive, and we still found nothing, then the absence carries real weight, suggesting that the thing is genuinely absent or rare. But if the search was limited, if our methods could easily have missed the thing even if it existed, then the absence tells us little. The strength of a negative result depends entirely on the sensitivity of the search that produced it. A failure to detect something with insensitive methods is not informative, while a failure to detect it with highly sensitive methods is. Understanding the sensitivity of our methods is therefore essential to interpreting what their failures mean. For the deep geological record, the sensitivity of our search is low for all the reasons examined throughout this inquiry. The record is incomplete, biased, degraded, and in many cases entirely destroyed. Our ability to detect a brief ancient signature within it is correspondingly limited. This means that the failure to find such a signature is a weak negative result, telling us little about whether a civilization existed. The methods are not sensitive enough for the absence to be meaningful. This is the core conclusion of the Silurian hypothesis as a piece of reasoning. It is not that civilizations existed, but that our means of detecting them in the deep past are too weak to support confident conclusions either way. The question remains genuinely open, not because there is evidence on both sides, but because the evidence required to settle it cannot survive. This conclusion has a curious and important reflexive quality because it applies to our own civilization as much as to any hypothetical ancient one. We have seen that our own signatures, clear as they are now, face uncertain prospects for long-term survival. The stable carbon shift may endure, but the nuclear isotopes will decay, the plastics may transform, and the physical structures will erode. Across tens of millions of years, our own civilization's signature would be reduced to a faint and ambiguous residue, difficult to detect and difficult to distinguish from natural processes. If a future civilization or a future investigator were to search the record for evidence of us after a sufficient span of time, they would face exactly the same difficulties we face in searching for hypothetical predecessors. our existence too could become nearly undetectable, our signature dissolved into the same destruction that consumes all records. This is a sobering reflection because it means that the impermanence we have been examining is not just a feature of the distant past, but a feature of our own future. The reasoning extends naturally and powerfully to the search for life beyond our planet, which was, after all, part of the original motivation for the hypothesis. When we look out at the universe and find no clear sign of other civilizations, we face the same logical problem in an even more severe form. The silence we observe could mean that civilizations are rare or absent, but it could also mean that civilizations exist but are undetectable, their signatures too faint, too distant, too brief, or too thoroughly erased to reach us. Just as the deep past of our own planet could hide a civilization without our knowing, the vast reaches of space and time could hide many civilizations whose traces we cannot detect. The silence of the universe, like the silence of the deep past, is ambiguous. It does not straightforwardly mean that we are alone, because our ability to detect others is limited in ways we are only beginning to appreciate. This connection between the deep past and the distant cosmos is what gives the Silurian hypothesis its broader significance. It began as a question about Earth's history, but it is fundamentally a question about detection, about the relationship between what exists and what we can know to exist. The same limitations that prevent us from ruling out ancient civilizations on Earth prevent us from ruling out civilizations elsewhere in the universe. In both cases, the absence of evidence is a weak result, because the processes of destruction, distance, and time degrade the evidence faster than it can reach us. The lesson is the same in both domains. We must be humble about what our failures to detect actually mean, and we must resist the temptation to read certainty into silence. The universe may be empty, or it may be full of traces we cannot read, and our current methods cannot reliably distinguish between these possibilities. There is a deeper philosophical point embedded in all of this concerning the nature of evidence and the structure of reality. The things that exist and the things we can detect are not the same set. There is always a gap between what is real and what is knowable, and the size of that gap depends on the sensitivity of our methods and the durability of the evidence. For much of the past and much of the universe, that gap is enormous. Vast stretches of reality lie beyond our ability to detect, not because they are hidden in any deliberate sense, but because the natural processes of destruction and distance place them beyond reach. Recognizing this gap is essential to thinking clearly about the past, about life elsewhere, and about our own place in a universe whose evidence is so easily lost. The Silurian hypothesis, in the end, is a meditation on this gap, a reminder of how much of reality may lie permanently beyond our knowledge. This realization invites us to turn the question outward in earnest, away from the deep past of our own world and toward the other worlds that fill the universe. If our own planet could hide its history so effectively, then what might other planets be concealing, and how would we ever know? The same reasoning that applies to Earth's deep past applies, with even greater force, to the distant and largely unexplored worlds that orbit other stars, and even to our nearest planetary neighbors. The possibility that those worlds might hold the erased remains of life, or even of civilizations, is the natural extension of everything we have considered, and it transforms the Silurian hypothesis from a question about Earth into a question about the universe as a whole.